Okay, so this lecture is about Urysohn lemma. And this Urysohn lemma is the deep theorem for this series. And the reason we call it deep because it involves many original ideas, comes from the mathematician Urysohn. And in fact, the Urysohn lemma and the Urysohn metrization theorem is his PhD graduation thesis, one of his essays he published in the early 19th century. And we were going to talk about Urysohn lemma for this lecture, and we will use it to prove two important theorems. One is the Urysohn lemma to prove the Urysohn metrization theorem, and the second we're going to prove the Tietz extension theorem. Okay, so let's just first give the statement of the Urysohn lemma. So the Urysohn lemma states that given a normal space and any two disjoint closed sets in X, and for any closed interval in R, okay, then there exists a continuous map from X to AB such that F maps A all to single point A and F to B all to single point B. So this is the statement of Urysohn lemma. Okay, so basically what it means is that it can separate two closed sets by a continuous function. So instead of proving this right away, we're going to discuss something that is based on the Urysohn lemma, okay? So we're going to prove it a bit later. So right now, a remark. We see that any two closed interval is homeomorphic with the closed interval from 0 to 1 via the map this explicitly given. And it suffices to check the case of 0, 1, right? It suffices to check the case 0, 1. Okay, and also motivated by Urysohn lemma, we have that for any space and any two closed sets in X exists a continuous function that separates them, then we say that A and B are separated by a continuous function. Okay, and the remark is that if A, B are disjoint closed sets can be separated by open sets, then Urysohn lemma implies this really just means that it's normal, right? Then Urysohn lemma implies that it can be separated by a continuous function, and the converse is also easy to see. So suppose we have such map F to be given, then this is open in 0, 1, right? This set is open in 0, 1, and the pre-image of this contains A, right? This is also open, and it contains A, right? Because F is continuous, and similarly for this, and those two are disjoint, right? So a disjoint open set, this contains A, right? This contains A, and this contains B. Okay, so the converse is also easy to see. All right, and one question arises, you might ask, is that why can't we just assume F is a regular space? Why we need normal space? Why we need normality to make sure that the Urysohn lemma holds, right? So there's a question, can we still separate a point from closed sets by a continuous function? Okay, so to answer this question, let's just see the proof of the Urysohn lemma first. Okay, so we're going to prove it, the Urysohn lemma. So step 1, we're going to construct a collection of open sets indexed by the rational numbers to define a continuous function F. So let's see how we're going to define the collection of open sets. Okay, so let's just first look at the rationals between 0 and 1 in the real number line. Okay, all those rational numbers. So let this set be P, and we want such collection, right? We want such collection, each is open in X, and if P is less than Q, then the closure of UP is contained in UP. So we want such collection, right? As P is countable, right, we can let 1 and 0 be the first two elements in the sequence. And we define U1 as a closed set is an open set, B is closed, okay? U1 is the open set, right? Which means that A is contained in U1, right? It's an open set, right, contains the closed set A. Hence, by normality of X, we can pick another set U0 open such that A is contained in U0 and U0 closure is contained in U1. This is the lemma for normality, okay? Okay, so the first two elements are defined. U1 and U0 are defined. Now we want to inductively define all our UPs. So in general, suppose Pn consists of the first n rationals, and we have this holds, right? The desired property you want is that P less than Q, then closure UP is contained in UQ, okay? And we let R be the next rational in the sequence, and we should define UR, okay? So let Pn plus 1, right, union adjoin this the number R. Oh, okay. So right now, we see that this is a finite set. No matter what, this is a finite set. Then we can pick P, Q, right, strictly less than R, and Q strictly greater than R, right? And there's no other points that is between P and R. No other points between them. No other rationals sits inside, right? So it's basically, you can picture this as R, P, and Q, and all the other points are somewhere else. This is doable because this is finite. It's a finite set, right? Right, and also because R is not 0 and not 1, because 0 and 1, right, is the upper bound, strict bounds for the set P. Okay, so now, given from this we can see that this is true, right, by inductive hypothesis, and because X is T4, so we can find UR, right, from here. We can find this is a closed set contained in an open set. And by normality of X, the UR kicks in, right? And we can do this by the lemma of normality. So this is why we require such weird assumption that the closure is contained, because we want a closed set contained in an open set, so we can introduce a new open set such that blah blah, these two are true, right? Okay, such UR definitely exists, and we want to see that this condition holds for all other two indices in this set, right? And it's easy to see, right? For S, right, if S is less than or equal to P, S is less than R, so we have this is true. And if S is greater than or equal to Q, then we have those two, and we're good, right? We just have to check R is one of them. Right? So we have successfully define our open sets. Is defined, and we wish to extend the definition to all of rationals. Okay, so to extend the definition to all of rationals, for P is negative, we define it as equal to 0, and if it is greater than 1, we define it as the entire space. And with this definition, this still holds. Okay, trivially to check, right? Okay, so we have defined our open sets indexed by rational numbers. Actually, in fact, you can see that any countable sets will do, right? Any countable sets will do. So now we're going to use them to define our function f. So for any x, we let qx be all the rationals that contains the up contains x. Be all the p such that up contains x. And we see that if q is negative, q is not in qx, right? Because x is never inside an empty set, right? So it contains no negative numbers, and also it is not empty because u2 is equal to x, right? I mean, right? So it is non-empty set that is bounded below, which means that we can define the infimum of this set, and we define x, f of x, as this infimum. Okay, so this is the rigorous setup. Okay, well, from now, it turns out that the f function is the function we want. Let's just verify this. So let's just verify a condition on the inputs, on the outputs. For x and a, because a is in U naught, containing U naught, right? We've defined this at the very beginning, right? And remember, U1 is x minus b. A is contained in U naught. Okay, so A is in U naught, so QX, A is in U naught, then it is contained in every single P that is non-negative, right? Because everything else is, of course, contains U0, right? It is indexed like that, right? So QX consists of all the non-negative rationals, which means that the infimum is 0, right? The infimum is 0, and you have to check this quickly. I'll give you 10 seconds to check it, and f of a, right, will then be equal to 0, right? All of f of a, right? For x and a, fx is 0, 0. So f of a is equal to 0, okay? And similarly, we have fb is equal to 1, right? Fx and b, remember u1 is x minus b. So if you're in b, if you're less than or equal to 1, then you're not in uq, right? Because you're in b, then you're not in u1. For q less than or equal to 1, uq is definitely contained in u1, right? If x is not in u1, it is also not in any subset of it, right? So if q is less than or equal to 1, it is not in uq. So q of x, for this q of x, it consists only the entire space, right? Only the entire space. Only the, P that is strictly greater than 1, that contains x. So the infimum is equal to 1. So f of b is equal to 1, right? So we have checked its condition output. And step 3, we're going to show these two elementary facts to prove that f is continuous. Remember, we have to prove that f is continuous. We're going to prove these two first. Okay, so the first one is that if x is not in u r bar, then fx is less than or equal to r. So if x is in u r bar, then you are in any us for s strictly greater than r, right? By the star condition. Thus, fx is less than or equal to r. Infimum is less than or equal to r. Why? So we have if s is greater than r, then x is in us. So for this r, we claim this is true, right? So suppose that we have this. Suppose r is strictly less than the infimum, then we can pick a rational s that sits between them. Now, s is greater than r, so x is in us. X is in us implies x is in qx, right? It is in the set, which means that, you're strictly less than the infimum, which is clearly a contradiction, right? So we have x is in qr bar, then fx is equal to r. Okay, first one, then we're done. Now let's look at the second one. If you're not in ur, then you're greater than or equal to r. If you're not in ur, then you're not in us for any s strictly less than r, right? If you're not in ur, then you're not in any subset. So if x is in us, then s must be greater than or equal to r. This is by contrapositive, right? Like s less than r implies x not in us, which means that if x is in us, s must be greater than or equal to r, which means that it is bounded below by r, right? It is bound, the set qx is bounded below by r, And because infimum is the greatest lower bound, so it must be greater than any of its lower bound. Okay, so, and this is equal to fx. So fx is greater than equal to r. Okay, so we have proved these two facts. And finally, we will show the continuity of our function f. And after this, we're done. So let's just finish this. So for what we want is that for x naught and x and f, for any neighborhood of f of x naught, we want to find a neighborhood of x naught such that f of u is contained in CD. This will show the continuity of f. And to do this, we have this. We can pick two rationals p and q between them, right? And between the p and q, we define the open set uq minus up bar. uq minus up bar. Okay, uq minus up bar. And this is an open set, right? It's open set intersect with an open set, right? X naught is in U, right? Why is X naught in U? Because this, right? Okay, let's just look at above. F of X naught less than Q implies X naught is in UQ. Remember, we have, if you're not in something, then you're greater than or equal to something. By contrapositive, this implies this, right? And similarly here, right? So, yeah, X naught is in U. So here's the picture to visualize this, right? X naught is between like those two, right? And the f of x naught is between them, right? And for any point that is inside, any point that's inside is in the subset of this, right? Because if x is in U, then first of all, you're in UQ bar. If you're in UQ bar by 1, fx is less than or equal to q. And also, you're not in UP bar, then you're not in UP. If you're not in UP, again, we have this strictly greater than p, right? So f of u is contained in this, is contained in this. So we're done. Okay, so we have finished the proof of Urysohn lemma. So now let's answer the question: can we prove this if x is only regular? So let's just do it. We pick a point A, and A is not in B, B is closed. Define U1 as x minus B, and U not neighborhood of A such that U not contains in U1, right? This is done by regularity of F. But remember, in the proof, I just copied directly. Let R be the next rational sequence to define UR, right? Such that if I we given this. And because x is T4, so we can find open set UR such that those two are true. And this is where we use the normality, right? And regularity cannot do this, right? For our case, for the new p, right, between 0 and 1, the third rational p, right, for our first and second is like 0 and 1, or 1 or 0. We have U bar not containing U1, right? We want to find open UP such that these two are true, but only regular space can do this. Sad, right? So, yeah, regular is not enough for Urysohn lemma. To separate points from closed sets by continuous function is in fact stronger than regularity and is weaker than regularity. Right? So, yeah, if we can separate closed sets, points from closed sets by continuous function, then we can separate them by open sets, right? This is, our reasoning was like here, right? Right, these two are the disjoint open sets, right? So in fact, separate points from closed sets by continuous function is stronger than T3, weaker than T4. And someone just call it like t of 3, 1 over 2. Because it sits between t3 and t4. And we say that space X is completely regular if it is t1, first of all, and for any, right, it can separate, like, exists continuously. Let me have to emphasize continuous. Exists continuous F that separates X naught and A. Okay? And the theorem, the completely regular behaves well with taking the complete regular behaves well with subspace and products. Okay, this is the theorem. For any subspace of completely regular spaces is completely regular, and a product of completely regular spaces, the product topology, it is also a completely regular space. And let's just prove it. For Y a subspace of X, right? First, we pick X naught and Y, and X naught and A for A closed in Y. A is closed in Y, which means that the closure of A and X intersect with Y is equal to A, right? So X naught cannot be an A closure. Now, we're back to the big space X. So we can pick a continuous function F such that f x naught is in 1 and f of A bar is equal to 0. What we need to do now is to restrict this domain to space Y. And it's still a continuous function. Okay? Restricting domain is still a continuous function, provided that your f is already continuous. And we just verify our output conditions. F of restrict Y x naught, because x naught is in Y, right? So this equality holds, and this is by here. And this, because A is, which means that A is a subset of Y. So these two are the same. And from this equality, we have this equality. And this is because this is this is also obvious. And this is equal to 0, right? And this also, in fact, shows that this is equal to 0, right? Because we can fix an element in A such that, right, if it can fix an element in A, then you're in A bar. So f of x is equal to 0, right? F of x is equal to f, right? I've been skipping, but it's also true. So, right, f of A is equal to f, right? So yeah, so we have this. So we're done, right? So we're done. And to verify the product, let X be the product space. Pick a point B in the product space, and A is closed in X, and B is not in A. Then pick a basis that's neighborhood of B. It is disjoint from A. Right? This is definitely true because B is not in A. Then you're in some open set, right? Then you can pick a basis element, right? That is disjoint from A. And okay, so for this product of U alphas, for those of U alpha that is open in X alpha for only finitely of them, right? For each them, we can apply the completely regular property of each of the spaces. So for I is equal to 1 to n, we define fi as the function from X alpha I such that there's B alpha I is equal to 1 and the X minus U alpha I, right? This is a closed set and it does not contain B because, right? So here, right? Okay, so it's equal. Now we define phi x as the projection of alpha I composed with this fi. So this is a function from x to 0 to 1. And this is a composition of continuous function, which is continuous. Okay, now we also see that for x is not and here, right? For x is not in this set. This means that x is alpha I is not in U alpha I, which means that phi I x is equal to 0. So phi I vanishes outside of all those sets. Okay, so keep this in mind, right? Keep this in mind, right? I mean, this is equal to 0, right? So phi x is this. Okay, so what we're gonna do is we define the function f as the product of those phi 1 to phi n. And this product is actually continuous by our lecture from metric topology. Our metric topology, so first we see that the operations, those operations is a continuous function, and the addition, right, if your codomain is the real number, then your addition, subtraction, I mean the sum and the products of continuous functions continuous. So here we have a product of continuous function, which is again continuous, right? And so first we see that f of b is equal to 1, right? Because b is in all those, right? U alpha i's, and here, right? F of b alpha I is equal to 1, right? This will be a 1 times 1 times 1, right? Because each is b alpha I, right? F of b is equal to this, right? Fi of pi alpha I of b will be equal to Fi of b alpha I, which is equal to 1, right? So yeah, as I already claimed, it's equal to 1 times 1 times 1, right? F of b is equal to 1. And outside of this open set, which is in the closed set, right? In the closed set, x minus product u alpha, in this closed set, we have this, which means that you are not in the u alpha i's for some I, right? This is true because you're not, for those u alpha that is equal to the entire space, right? We can't say anything. All we can do is to analyze those alpha I that is open and open in x alpha i's for some of them. So if we have this for some I, then this phi ix will be fi of f of alpha I. But f of alpha I is not in u alpha I, remember? Which this is true. So f of x is 0. So inside the product, some of them will be equal to 0, right? Fx will be 0. And A is a closed set that is contained in this closed set, so f of A will also be equal to 0. Okay, so this is the proof of the product of completely regular spaces still completely regular. Okay, so this is some Urysohn lemma and some notion of completely regular. And next time we're going to prove the Urysohn metrization theorem. And I'll see you guys next time.